Can you guys hear me okay? Y'all seem really scared and depressed right now. Like it's so quiet in here. Okay. So we're gonna be doing the 2017 exam today. The link, you can just go to the Weebly website if you haven't pulled it up already. Okay. So we're gonna get started with nomenclature. So for this exam, you'll need to know alkenes, alkynes, and alcohols. And the other stuff from exams 2 and 1, although those weren't really functional groups. So getting started, we have this linear chain with a couple of double bond and triple bond, and then we have a cyclohexyl group. So the cyclohexyl group doesn't have anything on it, so we're going to go with the chain that has the double and triple bond in it. So we're just going to start numbering. I'm just going to start from left to right. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then going the other way, 3, 4, 5, 7. So going from left to right, we get our triple bond on 2 and our double bond on 7. Going from right to left, we get our double bond on 2 and our triple bond on 7. So the numbers that start the double and triple bond are going to be the same going either way. So the next step in this case is we're going to go to giving the double bond the lower number. So if you want to review the alkyne and the alkene nomenclature, which I highly suggest you do because it is pretty subtle differences between them, this is what you're going to want to look at. And that's where I find the rule that I just stated. So whenever the double and triple bond fall in the same number of carbons going either way, we're going to give the lower priority to the double bond. So that means we are going to number from right to left like we did with the red numbering. So our parent chain is going to be 9 carbons, so it's going to be a nonane. And then because we have a double and a triple bond, we're going to put those in the name, and we're going to indicate the carbons they start at. So we're going to go 2 non-ene, and then our triple bond started at 7, so that's going to be 7-ine. And so that's going to be our parent section, I guess. So then our substituents, the only one that we have is going to be this group coming off of carbon 5. And this is a cyclohexane, so it's going to become a cyclohexyl. Again, carbon 5, cyclohexyl. And it doesn't have anything else on it like substituents, so it's literally just going to be 5-cyclohexyl. And then the next step is to do stereochemistry. So stereo is going to apply to double bonds or chiral centers. So we don't have any chiral centers in this molecule, at least that's not given to us that we could identify. But we do have a double bond over here on the right, and it has on the right side, we have a hydrogen going up top and a methyl going to the bottom. So obviously methyl is going to be higher priority than a hydrogen, so the bottom will be our star. On the left side of the double bond, we have a hydrogen bottom and we have the rest of the carbon chain on the top. So obviously the rest of the carbon chain is going to be our priority. So since our stars are on the opposite side, this is going to be E stereochemistry. And now that we've done our parent subs and stereo, we can just put it all together. So our name is going to be E5-cyclohexyl. And then 2 non-ene, and then 7-ine. Alternatively, since for our double bonds, we do have 2 hydrogens and 2 non-hydrogen groups, we could also label this one as cis or trans. And that only applies whenever we have 2 hydrogens off of that double bond. And so since the groups are on the opposite sides, you could label this one as trans. So you could put E or you could put trans and then the rest of the name. Any questions on that first one? So first we identified where the numbers started our double and triple bonds. We found that they were the same. So then the next step from there, this is in chapter 9, page 2. This lists the alkyne rules. And so I believe it's rule 2 or 3 in the notes. It says if the numbers are the same either way, the priority then goes to the double bond. So in that case, we'd give the double bond the lower number. And so that would be numbering from right to left to give the double bond 2 versus 7. Yeah, and that's only whenever the numbers are the same from either way. So if, for example, it was 2, 7, but then the other way it was like 1 and 6, then we'd go with the 1 and 6. Yeah, yeah. Mm-hmm. That actually is, I don't think that is true. Because in this case, if we had numbered from left to right, that would have given us, it would have given us 2 and 7 for the double and triple bond. But then our stereo, or not our stereo, our substituent would have been on carbon 4 instead of 5. So the way that we numbered here, we put it on a higher number, but the rule is not the substituent. The rule is between the double and the triple bonds. If they're the same, the double gets lower. No, if you go backwards, it's going to be, oh, sorry, you're right. Never mind. Yeah, okay. But it still would apply to the double bond thing first. And so again, I highly recommend you look at the alkyne and alkene nomenclature before you get to the exam, because these differences are very subtle. And this section right here that I listed, it explicitly states these kinds of differences that you'll need to watch out for. Yeah, you could have done cyclohexyl non 2-ene 7-ine. So that would have been, yeah. Okay, I'm going to go ahead and move on. So nomenclature number 2, we have a benzene ring with an OH, and then we have a linear chain with an OH. So for this one, I'm going to number the linear chain and the ring just to see how many carbons we have. So 1, 2, 3, 4, 5, and then we get to the substituent versus the cyclohex. Oops, that's not how you count. Versus the benzene. Benzene has 6 carbons. So in this case, the benzene part is going to be our parent because it has an alcohol and it also is a longer chain. So it's 6 carbons versus the linear chain, which was 5 carbons. And so as we discussed yesterday, anytime we have a benzene ring with an OH on it, this is going to be called a phenol group. And if you really wanted to, you could do the IUPAC naming where you do like 1, 3, 5 cyclohexatriene or whatever. But just do phenol. I don't even know if you'd get points for the alternative nomenclature. So just do this. It's a lot easier. So we've identified our parent chain as phenol. And then our only substituent is going to be the linear chain that's coming off of carbon 4. And so this is going to be a complex substituent because it has a substituent itself. And so remember that anytime we start naming a substituent, we have to number from the carbon directly coming off of the main chain. So that's why we're going to start over there on the left. So 1, 2, 3, 4, 5. So this is going to be a pentyl group. And because it has a triple bond, it's going to be a pentynyl. And the triple bond starts at carbon 3. So 3-pentynyl. And then we have a substituent on our substituent, which is this OH group. So remember that anytime OH is a substituent, it's going to be called a hydroxy group. So for this one, we have a hydroxy group on carbon 2, so it's going to be 2-hydroxy. And then 3-pentynyl. And then that's all going to go in parentheses because it's a complex substituent. And then we're just going to put all this together. We don't have any stereochemistry. We don't have stereochemistry on sp2 carbons. Triple bonds don't have stereochemistry, and we don't have any wedges or dashes on this carbon that we could use to identify stereochemistry. So this one, we don't have to do stereochemistry. We're just going to put it all together. So 4-parentheses 2-hydroxy 3-pentynyl. And then our parent was phenol. Any questions on this one? The only substituent that we have on the pentynyl is going to be hydroxy, so that one's going to be first. The yne is within the pentyl part, so yeah. Yeah, so if we had like a methyl, then we'd do based on alphabetical and put it together. Any other questions on this one? Okay, moving on to our last nomenclature. So for this one, we have a couple of double bonds and we have an alcohol group. So for this one, we're going to have to remember that our alcohol is going to be our highest priority group that we know so far. So this is going to get, the alcohol is going to get priority over the double or any triple bonds that we might have. And so we're going to number the chain starting from the side that would give us the lower number for that parent. So we're going to start numbering from the top. So 1, 2, 3. And then if you guys will notice, this is symmetrical. So if we go to the left or the right, it'll be the same. So I'm just going to go to the right. 6, 7. So that means the other half is going to be a substituent. So we have a 7-carbon chain. So this is going to be a heptane. And then we have a double bond that starts on carbon 6. So this is going to be a hept 6-ene. And the OL will be our suffix for the alcohol parent, and that's on carbon 2. So heptene 2-ol. And then for our substituents, we have the group coming off to the left. So 1, 2, 3, 4. So this is going to be a butyl. And then because of that double bond, it's going to turn into but 3-enyl or 3-butenyl. And that's our only substituent. So next we just have our stereochemistry. So for the 2 double bonds that we have, you'll notice that they each have the same group on the end. So they both have hydrogens on that end carbon. And so since those 2 groups are the same on that side, we can't do any stereo with those double bonds. But we do have wedges and dashes here at carbon 2, so we're going to have to look at the stereo for that carbon. So for stereo, OH is going to get our highest priority because it is a larger, a higher number on the periodic table. For our hydrogen is obviously going to be our lowest, so that's going to get 4. And then we have to compare the groups going down and then going up and to the right. So we're going to look at the next adjacent atom. So those are both carbons, so then we have to move on. The group to the top right is just connected to 3 hydrogens. So this one's going to be H, H, and H. And then the carbon at the bottom is connected to a carbon to the bottom left, a carbon to the bottom right, and then it also has a hydrogen. So between CC and H and HH and H, the bottom one has higher numbered atoms on the periodic table, so we're going to give that one our next highest priority. So that will leave the group at the top right to be our third priority. So just to rewrite the numbers, we have 1, 2, and 3. So we're going to have S stereochemistry. And then we don't have to flip it because our lowest priority is on the dash, so that's good to go. And so that's going to be our stereochemistry. Putting it all together, stereo is S. Our substituent was this 3-butenyl, and that was coming off of carbon 3 on the main chain. And then in parentheses, 3-butenyl. And then our parent name was kept 6-ene-2-all. Any questions on that one? Mm-hmm. Yes. Yes. No, it would still go out at the front. Mm-hmm. Yeah. Any other questions on that one? Oh no, you're right. So there doesn't have to be a dash there. If you had done it, the 6-heptene-2-all, then you'd put the dash. Good catch. Any other questions on that one? Okay. Again, I tried to highlight the nomenclature portions that you guys will have to review for the exam. And I'll go ahead and give you guys my annotated copy after this so you guys can look back at those sections that I highlighted. So we're going to move on to our facts. So this one, you guys, for question 1, you guys already had this on your exam too. I'm just going to go over it really quickly just because. I did also point out for each of these the sections that you'll have to review. And then specifically chapter 9, page 2. We talked about this one yesterday with Hamza's review. There was one that had like a triple bond in a cyclic structure. So you might have to know that. I'm not sure if she would ask the same kind of question since it was on exam 2, but there is something that you'll have to know for Alkyne specifically about this kind of question. So you might as well review it. This one doesn't have any triple bonds, but again, I'm just going to go over it because I feel like it. So bridgehead carbons, this one's not a bridgehead because it's not at the connecting point. This one is, and this one is. So this one's going to be stable because it's not at a bridgehead position. For these other two, though, we're going to have to see how many carbons are in that chain to see if it's going to be stable. So we want 8 or more carbons. And it's the same rule for alkynes. For alkynes, you'd want a cyclic structure with 8 or more carbons for that triple bond to be stable. In this case, we have 1, 2, 3, 4, 5, 6, 7. So this one's going to be unstable. And then this one, 1, 2, 3, 4, 5, 7, 8. So this one would be stable because there's enough carbons in the chain to kind of alleviate that ring strain that's imposed on that bridgehead position. Yes. Yeah, like if it like asked you 1, 2, or 3 for stability, so like most stable, then this one would be the most stable. Actually, I would think. That's a good question. I wouldn't be able to give you a 100% answer because I haven't seen that question before. I would still think this one would be the most because the double bond is not in a bridgehead position, so it doesn't have any sort of ring strain other than just being a double bond in the ring, but that's not really that bad, especially because this is like a 7 or something. Yeah, so that's bigger than a cyclohexane, so I feel like that double bond would be pretty fine Whereas this one, it is 8 carbons, but it is at the bridgehead position, so I think that would be 2. And then this one would be 1, obviously, because it doesn't satisfy the 8 carbon rule. So that would be my thinking, but again, maybe not 100% sure. So, any other questions on this first one? Okay, so moving on. The next question that we have is electrophiles in order of increasing electrophilic character. And so Dr. Bean mentioned to me to kind of amend this. So she means at the carbon attached to the oxygen. So we're going to be looking at the electrophilic character of those specific carbons. So chapter 10, page 2 could be helpful for this. So electrophilic character just means it's going to be positive or partially positive. And so we know that whenever we have a carbon attached to something that's electronegative, such as an oxygen or a fluorine or a chlorine or something, that electronegativity difference kind of pulls some of that electron density away from the carbon. So it makes the carbon partially positive, and then whatever the electronegative atom is, slightly negative. So we're going to want to find basically the most partially positive carbon that we have. So we want stuff that pulls away, so want stuff that pulls electron density away. And so again, that's going to be electronegative atoms, so for this first one, we have an OH. So there is a little bit of difference between the carbon and the oxygen. In the middle, we have a double bonded oxygen. And then we have chlorines going to either side. And then on the right, we have just a double bonded oxygen without anything else. And so the rule for this is basically the more things you have to take away the electron density, the more electrophilic that carbon will be. So for this one, the most electrophilic is going to be here in the middle because it has essentially 3 things pulling away electron density. So this one's going to be the most partially positive. And then between the ones on the left and the right, you can kind of think of it as though the carbon on the left is only single bonded to the oxygen, whereas the one on the right is double bonded to the oxygen. So it's almost like having 2 oxygen bonds. So the one on the right is going to be our next most electrophilic, and the one on the left is going to be the least, just because it's just single bonded to that oxygen. Any questions on this one? Okay. If you guys want me to slow down too, just let me know. Mm-hmm. Yeah. So, yeah, of course. So, you guys might be a little bit more familiar with nucleophiles because we kind of talk about those more. But basically, electrophilic means something that is either fully positive or partially positive. And so an electrophile has this kind of partial positivity, whereas a nucleophile would be something that has a full negative or is like partially negative. So that's going to be like your lone pairs, double bonds, triple bonds, like full negative charges like we've seen with like some of our substitution reactions like CH3O- or something like that. So you might be a little bit more familiar with nucleophiles because we use those a lot for reactions and for mechanism. So electrophile is basically just going to be the opposite of that. So it's going to be something that is partially positive or fully positive instead. Yes. Yeah. That electron density is being pulled away. So that means there's less negative electrons. So that means it's going to be more positive. So the dipole moment versus just electrophilicity is slightly different. So even though the dipole moments might cancel out with the chlorine sides, it's still pulling stuff away from that carbon, so it's still going to be electrophilic. So the dipole might cancel out, but that carbon is still going to be partially positive. That's a good question. Yeah. Mm-hmm. So you're kind of getting into electron withdrawing groups and electron donating groups. So this is going to be a big thing in Orgo too. But yeah, so electron withdrawing groups are going to be what we're talking about here. So chlorines, like double bonded oxygens and stuff like that. So electron donating groups would be something that's like something that's not electronegative. So maybe let's say like just another methyl group. So if we had this question and it was this structure versus the one that we have in our question here, and we had to rank them. This one is more, this carbon right here, same carbon that we're looking at, it's going to be more electrophilic, whereas this one would be less electrophilic because this one doesn't have groups taking away the electron density. The methyls, carbon-carbon is like essentially the same electronegativity, so there's no difference. So these would be considered more of like an electron donating group because you just have like methyl groups around you. It's like having a bunch of friends around, so you're gonna have like more electron density. Whereas this one, you have like traitorous friends that are stealing your electrons, so you're gonna be withdrawing. Whereas methyls would be like donating. I'm gonna go ahead and move on for sake of time. But if you guys have any more questions about that, I will be happy to answer afterwards. So for the next question, we're looking at producing an alkyne, specifically terminal alkyne with NaNH2 at 150C. So for this one, we just need to identify if there's an end position that can form a triple bond. And so by that, I mean, not only do we need two halides like we have in the elimination mechanism for that reaction, we also are going to need two hydrogens because each formation of the double or triple bond is going to be minus the halide, and then the next one is going to be minus, it's going to be minus the like HX, and then the next one's going to be minus another HX. So if we don't have enough hydrogens adjacent to where we're trying to do the elimination, then we won't be able to do the elimination. So for this first one, we have the chlorines on the end. The adjacent carbon has two hydrogens, so this one is going to be a yes. For the next one, we have two halides, but on this carbon, we only have one free hydrogen that we can use to do an elimination. So this one is going to be a no because we'd only be able to remove one equivalent of HX. And for this one, we'd only be able to form the double bond. If we tried to do a another elimination, we would get something like this. And this carbon would have now 5 bonds, which is obviously not reasonable. So this one's going to be a no. So it can help if you like want to try and draw it out and see like what the triple bond would look like and if it makes sense. So for the next one, we have two bromines, and these ones are in the middle. However, if you guys remember that NaNH2 specifically, it does the rearrangement. And so this one is pretty much always going to form a terminal alkyne if possible, just because of that rearrangement mechanism. And so if we look at this structure, we notice that on the ends, we kind of have we have like this free chain floating out. And that carbon on the end does have 2 hydrogens that we could take off. This one does 2, this one has 3 now. So these ones do have plenty of hydrogens that we can use to form the elimination reaction. So this one's going to be yes. So if you wanted to draw out and kind of see what that would look like, you'll see, okay, this is going to be my triple bonds. And this makes sense. This carbon does not have too many bonds. This one does not have too many bonds. So we'd be good to go on that one. And for this next one, we have our chlorine here and here. So we have this kind of structure without the chlorine drawn in. So this one is going to be a no, because although we have 2 chlorines and we're kind of at an end right here, remember that this carbon has a methyl group going up at the top. So we wouldn't be able to form a triple bond like this, because then this one would have too many bonds. So this one's going to be a no. Any questions on that one? Yeah, sorry. Mhm. Mhm. In this case, we wouldn't be able to, because the methyl group here is kind of like splitting the it's kind of splitting the chlorines across that carbon. And what I mean by that is the mechanism won't be able to do that rearrangement. So I guess I don't want to draw out the mechanism right now because it's pretty long. But I can go over it with you afterwards if you'd like to see that. But it's also in this section right here. So that kind of details the mechanism that would do these rearrangements. We'll go ahead and move on. For this next one, we have place compounds in order of increasing oxidation state. So this is going to be chapter 11, page 1. And so increasing oxidation state basically just means more oxygens. It's a little bit different than I think the general chemistry mechanism or definition. So don't get tripped up by that. Try to think of it in the organic chemistry aspect. And again, I point to chapter 11, page 1 for that. So we're just going to look at the carbon that has the most oxygens. So for this first one on the left, this carbon essentially has 2 bonds to oxygen. The one in the middle, it's just single bonded to oxygen, to the OH. So this one's going to be like 1 bond. And the one on the far right, we have 2 bonds here with the double bonded O, and then we also have the OH coming off of the top. So this one's going to be an additional bond. So it's like 3 bonds total. And so again, increasing oxidation state, we want more bonds with oxygen. So the middle is going to be our lowest oxidation state. The one on the left is going to be our intermediate, and then on the right is going to be our most oxidation state, or highest oxidation state. Questions on this one? Okay. Okay, this is a Grignard question. This one is slightly different than the one that we looked at yesterday in Hamza's review. So I highlighted and make sure for this exam you read your instructions, because she got y'all good with the last exam on the synthesis with like the butene or whatever. So read your instructions, please. But for this one, we have react with a Grignard reagent. And the one yesterday, it was form a useful Grignard reagent or something like that. So they are slightly different. And you kind of get a hint when you look at all these structures. We don't see any halides. So that might be a little bit confusing, but just remember to read your instructions. So essentially, we're just going to see what of all of these compounds will react with the Grignard reagent. So we're not thinking about like trying to do synthesis and forming like a proper product. We're just seeing what can or cannot react. So for this one, Chapter 10, page 6 and 7, this one highlights all the stuff that a Grignard reagent will react with. But basically, it's going to be any acidic hydrogens, so our NH, OH, SH, and then also electrophilic carbons, so like things that are double bonded. So we have double bond oxygens, we have double bonds nitrogens. Another one to know is any nitro groups, which are going to be nitrogen with a couple of oxygens on it, and sulfur double bonded to oxygen. So I'm not sure if I got all of them, but again, just look to this section to kind of review that. And so we're just going to go through and see, oh yeah, I forgot, terminal alkynes, that's another one. So we're just going to see what can react. So for this first one, we have a double bonded nitrogen. And so for this one, if we look at our list, we have a double bonded nitrogen as something that would react. So this one's going to be yes. For the next one, we have a terminal alkyne. So this one has a acidic proton, which will react with the Grignard. So this one's going to be yes. Please note that the terminal and internal alkynes are different. So an internal alkyne would not react because there's not an acidic enough hydrogen. Whereas for the terminal, the hydrogen that's directly connected to that triple bonded carbon is acidic enough. So this one's going to be acidic. So for the terminal, the hydrogen will be acidic enough to react. But for the internal, there's not an acidic hydrogen, so it would be no. So there is a difference between internal and terminal. For the next one, we have a double bond. And although the double bond does have hydrogens, double bonds are not acidic, or their hydrogens are not acidic enough to react. And carbon-carbon double bonds, they're also not reactive enough to react with the Grignard. It's just like double bonded two atoms that are different in electronegativity. So double bond O or double bond N or something like that. This one's just double bond C, so this one's going to be no. For the bottom left, we have what's called an ether. So ethers are going to be oxygens that are bonded to a carbon on each side. And so ethers are pretty unreactive. They kind of just like chilling and doing their own thing. And there's not a hydrogen that's directly attached to the oxygen to make it acidic or to make an acidic proton. So this one is also going to be a no. So ethers, unreactive with Grignard. So for the next one, we have an SH. So SH, remember, is pretty much like an OH. Again, it's also in the list that we have up here. So this one is going to be acidic and it will react with the Grignard base. For the last one, we have a nitro group, which again is one of our functional groups that will react with the Grignard base. So this one is also going to be a yes. Any questions on this one? Mm-hmm. This one right here, the double bond. I mean, part of it is kind of just memorizing what is and what isn't, but there is also like the acidity rules. So for our carbanions, we looked at like acidity rules in like exam 1 and 2 question mark. So we looked at kind of like what these different carbanions would be in terms of acidity. And this might be earlier in the notes. I didn't go back that far to look between the carbanion acidity levels, but what you need to know is a triple bond carbanion is going to be I'm not going to say it's going to be a stable anion. Double bonds, not very stable. carbanions. And just regular alkanes are going to be even less stable. And so again, you can go back and kind of review those chapters on the carbanion stability. I'll look at my notes after this and see which chapter that is exactly. But it has to do with like the cardio rules. So orbital, the more S characteristic a bond has, the more stable that carbanion will be. So an sp3 bond is 25% S and 75% P, because S and then P3. sp2 is going to be 33% S and 66% P. sp, which is the linear, so a carbanion, a triple bond carbanion, that one's going to be 50% S and 50% P. So since the triple bond carbon has more S characteristic, the carbanion is more stable in that orbital, which makes it more acidic. But I'll find the actual like chapter and pages that you can look at, because they'll probably explain it better than I did. Any other questions on this one? Yes, so like if you're asked the question that we were asked yesterday, then you'd have to look and see if there's that kind of question basically asks if there's going to be one of these in addition to like the bromine you're trying to react with. And so in that case, you have to watch out, because if you have two functional groups, such as the bromine that you're trying to react with, and let's say like a terminal alkyne in the same structure, then you're going to get some side product, and probably mostly side product, which will ruin your reaction. Yeah, so if this was like the reaction that we looked at yesterday, or not the reaction, the question, then it would just be flipped basically. Mm-hmm. 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 Yes, so that's going to be in terms of like the compounds that you get, their structures, and the directions of the question. So what it says in the question. And so I mentioned at the beginning that for these compounds, we don't see any halides. So usually, like when we're doing synthesis, we need to have like our RBR group to react it to do our MGBR and then do our Grignard. But we don't have any halides on these compounds. So it's going to be asking something a little bit different. So that's kind of a hint, but then also just the directions that it says. I'm going to go ahead and move on again for sake of time. So we're going to get to our reactions now, goody. So if you guys are struggling with reactions, what I suggest is using the reaction sheet that like is from the SCP workshop. And if you don't have the PDF, I can give it to you. So it's basically just the list of all the reactions. So if you're struggling, I suggest practicing your reaction section with the printout of all the reactions. And first, going through a reaction and being like, okay, what's this reaction? Looking in the sheet and finding it, and then doing that reaction. And then as you keep practicing, slowly start to take away the cheat sheet so you can kind of test yourself on what you know. Because it's just too much to try and shove it all in your brain and not practice with the actual sheet. There's a lot of like little details about like stereochemistry and like anti-Mark versus Markovnikov that are on the sheet that really help when you're first practicing. But anyways, for this first reaction, we have an alcohol and we have H2SO4 and heat. You could also see it as like H2SO4 and 180C. So this is going to be the alcohol dehydration. So we're going to remove the OH and an H and form a double bond. And this one is going to be, not Markovnikov, this one's going to be Zaitsev's rule. So we're going to form the more stable double bond. So for this first reaction, we're just going to form the double bond in between those two methyl groups that are sticking out, because that's going to give us a tetrasub alkene. which is going to be the most stable product. So then the next reactions we have, steps 2 and 3 go together. Again, using the reaction sheet helps because you can see which reactions are coupled together. If worse comes to worse and you're on the exam and you have absolutely no idea what a reaction does and you think, I've never seen this before in my life, maybe it might be one of these coupled reactions. But again, using the sheet can help you identify them. So this one is called ozonolysis. So O3 is what it's the molecular structure for ozone. So this one splits the double bond, and it oxidizes where the carbon-carbon double bond was. I'm just gonna say it oxidizes those carbons. And this one is going to be mild, so it's only going to form aldehydes or ketones. And that just depends on the substitution of that carbon, if there's any methyl groups or hydrogens or whatever. So for this one, we're going to split here. And then we're going to put a double bond O in the place where the carbon-carbon double bond was. And in this case, we have 2 methyl groups. So these are both just going to stay as the ketone. We can't oxidize that any further. So then for this next reaction, this one is a acetylide anion. So acetylide. So what this one does is the lone pair attacks the carbonyl carbon, and that pushes the double bond O out and forms the O minus. And then the H3O plus step in the last step will protonate that oxygen to become a alcohol. And so we have 2 of these carbonyl groups, so we can do it to both of them. And so the end result is going to be alcohol, and then our acetylide anion. Any questions on this one? Okay. Again, if I'm going too fast, then just yell at me. Okay, next question. We have KOH 200C. So this one is going to be alkyne formation. And the other one that you could see, the one that we saw in the facts question, was NaNH2 and 150C. So these will both form the alkynes. The only difference is that NaNH2 will form terminal, so at the end, whereas KOH is going to form internal, or in the middle. So we're just going to form a triple bond. We're not going to form it at the end. We're going to form it in the middle. And since this one would be symmetrical either way, you could put it either there or where I drew it here. She shouldn't. Like, I don't know. I always got used to drawing it like that because I feel like this looks really stupid. But you could do either one. Yeah, I don't know. I just think it looks stupid, and I feel like it's easier to get lost the amount of carbons that you have, but I don't know. Okay, so reaction 2. This is going to be called dissolving metal reduction. Dissolving metal reduction. And so this one is going to turn our triple bonds to a trans double bond. So for this one, it's going to be trans, so we do need to show the stereochemistry. So we need to show that our hydrogens add to the opposite sides. And it's just going to stop there at the double bond. It's not going to keep going. for our last reaction, we have MCPBA, which is the epoxide forming one. Just so you know, this one could be any peroxy acid. MCPBA is the one that we talk about in class. I don't want to say she would be so mean as to do another peroxy acid to throw you guys off, but it's possible. So this is what a peroxy acid looks like. So MCPBA stands for metachloro benzyl peroxy acid or something like that. So it's just like an acronym. So it's a peroxy acid, and this is the structure. So if you see a structure like this, and you're like, what the hell is that? It's a peroxy acid, and it will do the epoxide forming reaction. But the epoxide is just like the little triangle with the O. And so this one, it retains stereochemistry. So we're going to show that our hydrogens are still on opposite sides and the carbon groups are still on opposite sides. So this should be accepted where you're kind of just drawing it in like the line and stick form. If you really want to be safe, just draw your hydrogen on a wedge and then the other one on a dash. For this one, there's not going to be any hydrogens on the triple bond. Oh, after step 2. No, you don't have to, but at the same time, it might be a little bit more difficult to see that you do the right stereochemistry. But that's like a TA grading thing. So, yeah. Any questions? Yeah. Yep. Yeah. So you can just, I don't know, I just like to draw the little, keep it same and then just draw the little oxygen. Okay, I'm gonna go ahead and move on. For our next reaction, we have BH3THF, and this one's also a coupled reaction. So step 2 is going to be coupled. And so this one is going to be addition of H and OH. So this one's going to be anti-mark, and it's going to be syn coplanar. So the H and the OH are going to add to the same stereochemistry. And so we have our chain going up top. This one's anti-mark, so the hydrogen is going to add towards the more substituted side. We're going to draw our hydrogen here. And then our OH is going to add to the other side of that double bond. And again, they're going to be syn coplanar. So you'll draw them on the same, either both dashes or both wedges. So then step 3, we have PBr3. So this one is going to replace the OH with a bromine. And so this one is SN2-like. And by that, I just mean it flips the stereo. So flips stereo. So our oxygen, or sorry, our alcohol, which was on the wedge, is going to be flipped. It's going to become a bromine, and it'll be on the dash now. Step 4, we have NaCN, CH3CN. So this one is going to be an SN2 reaction. Nitrile is a weak base, but strong nucleophile because it's negatively charged. And so SN2, it's going to attack where the bromine is. The bromine's going to leave, and then SN2 flips the stereo as well. So that CN is now going to be on the wedge. Questions on this one? Yeah. I'll leave it up here for just a second. Yes, so the PBr3 reaction will flip the stereo once, and then the step 4 with NaCN is SN2, so it's going to flip the stereo again. So we're going to end up with the same stereo that we had after steps 1 and 2. I'm going to go ahead and move on. Okay, steps 1 and 2 for this reaction. Hamza has an interesting name for this one if you want to ask him about it. But for this one, the cyanoborane reaction, this one also adds H and OH. It does anti-mark. And this one does an interesting mechanism. So first I'm going to draw the product. So the product is going to be an aldehyde. And so you might be wondering, how did we get to an aldehyde from adding an OH? And if you already know the answer to this, then sorry, but you have to learn it again. So for this reaction, we do add the alcohol to the less substituted position. We have the double bond, and then we added the hydrogen to the other carbon in the triple bond. So this is what's called an enol, and so that just comes from alkene and alcohol, so enol. And under normal reaction conditions, this is not a stable form. So this is going to undergo what's called keto-enol tautomerization. And I would definitely review this concept because she could ask you a facts question about this. I think in the past there might have been like a short answer question about this one. So definitely review it. I always look at like masterorganicchemistry.com. They're really good with lots of different stuff. So basically this will just undergo a rearrangement and it will eventually form the keto form. So the keto form could either be the ketone or it could be an aldehyde. And so the one that we did yesterday in Hamza's review, I think it did a similar reaction, except I think it was with the mercury reaction. So the mercury adds Markovnikov, and then that one forms the ketone, but it's the same concept. So just make sure you review this keto-enol tautomerization thing. Yes, so the triple bond will turn into a ketone or an aldehyde, depending on which carbon the alcohol is added to. So if this was the mercuric reagent, yes, so if this was the mercuric reagent, so Hg is mercury, then we would form the more substituted product, which is going to be the ketone form in this case. And I always remember the mercuric reaction because mercuric starts with an M, so it adds Markovnikov. Anyways, so that was 1 and 2. Step 3, this is a lithium reagent. So we have a aldehyde, so we have a carbonyl, and we have this lithium reagent. So this one is going to be Grignard-like. The organometallic reagents, so lithium or MgBr, which is Grignard, these ones will do the alkylation, where the alkyl part will attach at the carbonyl carbon. That pushes the oxygen to be O-, and then the H3O+ will protonate that to form the alcohol that we have in our end product. We're going to have the OH, we have the H, and then we added the CH2CH3. So then step 4, we have Na2Cr2O7. This one is going to be a strong oxidizer. And so this one is going to turn alcohols into ketones or carboxylic acids. In this case, since we have since we have a secondary alcohol, it's just going to form the ketone. But what we're going to get is H2, C, double bond O, H2, CH3. Any questions on this? Okay. All right, reaction 5. So this one we have LaAlH4, which is one of our reducing agents. And this one specifically is going to be our strong reducing agent. So this one, LaAlH4. So this one can reduce anything. So we have our ketone, aldehyde, ketone. We have our ester, which is going to be OR. We have carboxylic acid. And then we have acyl chloride. So LaOH4 will be able to reduce all of these, and so it takes these carbonyl carbons and it turns them into an alcohol of a various form depending on which one you have. NABH4 is the other reducing agent, and this one's weak, and it can only do ketones or aldehydes. In this case, we have LaLH4, so we can do whatever we want. And so what this one does is I suggest looking at the mechanism for this one because this one is kind of tricky, I think, to some people. But we're going to split the bond between the oxygen and the carbonyl carbon because in one of the first steps, the ester oxygen becomes protonated, so then it becomes a good leaving group and gets kicked out. And then we're just going to protonate the oxygens to be alcohols. I also suggest numbering your carbons. So on the top half, we have just one carbon, and then we have the oxygen. So this one's just going to be a primary alcohol. On the bottom, we had 1, 2, and then we get to our oxygen. So it's still going to be primary, but it's just a longer chain. So again, we slip the bond in between the carbonyl and the ester oxygen, which opens that ring, and then we just reduce the oxygens down to be alcohols. So then for the next step, we have NaOCl. And this one is also an oxidizer. This one's also just bleach. So commercial bleach is NaOCl. And so this one is notably a selective oxidizer. So depending on what alcohols you have, it might only oxidize one. So this reagent is going to be selective towards secondary alcohols and benzyl alcohols. So if there's these alcohols in your compound, this is what it's going to reduce. Sorry, this is what it's going to oxidize, and it's not going to oxidize anything else. So if you'll notice the alcohols that we have in the compound, we have this one at the bottom, which is a few carbons away from the benzene chain. So this one's just a regular primary alcohol. And the one at top is a primary alcohol, but it is a benzyl alcohol because it's one carbon away from the benzene. And so again, this reagent is going to selectively oxidize secondary or benzyl alcohols. So let me draw my arrow. So we're only going to oxidize the alcohol that was at the top. And the other one on the bottom is going to stay as the alcohol. Questions on this one? Yes. You mean like one LaAlH4, two equivalents of H3O plus or something? I would just think that that means that you have an equivalent to reduce or turn the OH for each into that alcohol. So for this one, we have two oxygens. So then you could do the reduction to both of them. I don't think there'd be a case where like you have something like this and then it's like one equivalent, because then it's like which one, you know? But that would be my thinking. Any other questions on this one? Okay. Our last reaction, we have this double bonds, and our first reaction is HBr. So this one is going to add H and it's going to add Br. This one's going to follow Markovnikov's rule. So this one is just simply going to add a bromine and a hydrogen. So then for step 2, we have Mg ether. So this is going to be, it forms the Grignard reagent. Grignard. So we're just going to turn the Br into MgBr. Then step 3, we have an acyl chloride, which is one of these groups that I mentioned up here. It's just the ketone connected to the chlorine on one side, and then H3O plus. So this is going to be a Grignard reaction. So this is going to attack at that carbonyl carbon. The oxygen is going to get pushed up and into the O minus. But then for this specific reagent, the acyl chloride, what's going to happen is the O minus is then going to come back down and reform the double bond and kick out the Cl. So draw it out for you a little bit. So we add the first equivalent, and then we have this O minus. So this is going to come back and form the ketone again and kick out the Cl, because chlorine is going to be a good leaving group. If you think of like our substitution and elimination reactions, chlorine, bromine, they're good leaving groups. So we're going to be left with this ketone. And now that we've reformed the ketone, we can do another equivalent of this Grignard to attack, kick up the oxygen. And this time we don't have a good leaving group. So after this second addition, it will just stay as the O minus and then eventually get protonated into the alcohol. God, this is hard to draw. So then our final product will just be this in the alcohol. My drawing kind of sucks, but yeah. Any questions on this? In this one or this one up here? Hmm? The benzene? I'm not sure about that one. Benzene is really stable because it's aromatic, which we'll get into in Orgo 2. So for the Raney nickel one, it'd probably just be one that has like a ketone and just a regular double bond in a linear chain. I don't think you'd see Raney nickel with a benzene, just because it's like something different. Yeah. Yeah. Any other questions on the one that we just did or any of the other reactions? Yes, it does. Yes, because they are both secondary carbons, but the position that I put the bromine at is the benzylic position, which is going to be more stable. So remember that in addition to like primary, secondary, and tertiary, we do have like benzylic and allylic carbocations and stuff like that. So in this case, the reason why we put it on the left was because the benzyl position is more stable. And that's a good question because she does put 0 points if you put it in the other position. So. Any other questions on reactions? Mm-hmm. So for Grignard, Grignard is going to react with, it's very reactive, so it's going to react with any like ketones or like those other functional groups that we talked about in the facts. But for this one, what happened was the carbonyl compound that we had a good leaving group on one side. So that's going to apply to it's going to apply to an acyl chloride like this one. So this would be a good leaving group. And it could also apply to esters. So if you had like an OCH3. So anytime you have a Grignard reaction with one of these compounds, the first equivalent is going to add like we did. It's going to form the O- like normal, but then because there's a good leaving group on one side, the O- is going to come back and kick out that good leaving group and form another equivalent basically that we can use to react. So then you just do the reaction again. So anytime you see a Grignard type reaction where you have like MgBr or like the organolithium reagent with one of these compounds, you're probably going to have to do 2 equivalents of that reaction. Yes. And it's not going to apply to carboxylic acids because OH is not a great leaving group. We know it would have to be like OH2, but it's, yeah, so it's just going to be OR or the Cl. Mm-hmm. Okay, I'm going to go ahead and move on to mechanism. Yes, so I'm going to go over this mechanism and this synthesis. And then if you guys want to stay, I'm going to do like a little bonus and do an additional mechanism and synthesis from a different exam, just for extra practice for anybody who wants it. So we're going to go over this one, and then I believe the one I pulled from was 2016. So we'll do that afterwards. Yeah, I'll record it and post it on YouTube because why not? Yeah, I'll post this after I finish annotating it to the teams. Yes. Okay, so for mechanism, I don't know. Mechanism is mechanism. So make sure to first identify your nucleophiles and electrophiles. So it's kind of given to us with the HOSO3 H. So we're kind of hinted that we're going to be taking this proton from the H2SO4. So we're taking an acidic proton. We just need to identify which nucleophile is going to take that acidic proton. So we have a double bond and we have an O, which has the lone pairs. And oxygen is the lone pair is going to be a stronger nucleophile. So in this case, we're going to have the oxygen take the proton away from the sulfuric acid. So in the first step, this is going to take the H, and that's going to be given back to the HSO4. So now we've protonated our OH, so now this is going to be a good leaving group. Water is a good leaving group. And so in the next step, we know that our water is going to leave, but if you'll notice, if we just draw the product of the OH2 leaving, we would have a primary carbocation. So primary carbocations are really bad. We hate them. And so what we have to do for this one specifically is we have to show a hydride shift as we're kicking the water out. So we're going to do the hydride shift, and we're going to kick the water out. So that's going to give us it's going to put the plus charge in this position, which is going to be a tertiary carbocation. And we like tertiary carbocations. So you would have to show this in the same step, just because primary carbocations are so unstable. So now we have this plus charge on this tertiary carbocation, and we see that we form an additional ring. So what we're going to do is we're going to have our nucleophile in the left cyclohexane, the double bond. This is going to attack that plus charge, and it's going to form that second ring. So I'm just going to number my carbons, make sure I have everything in order. So 1, 2, 3, 4, and then we're on the ring. So 1, 2, 3, 4. And then carbon 1 had the 2 methyl groups. So this is going to be our structure. So we've satisfied the plus charge that was here initially, but that doesn't mean that it's gone. So the double bond from the cyclohexane on the left, it kind of kicked out to form this new ring, but the carbon that did not get attached to the new bond is going to be our new carbocation because it lost the bond from the double bond. So now that we have this carbocation, we have 2 different products that we could form. So we have a double bond in between, and we have a double bond kind of going up and to the right. So these are just going to be a couple of elimination reactions. So for this first one, we want to form it in between the 2 cyclohexene rings. So I'm going to pull a hydrogen from the bottom. So HSO4 minus is going to be my nucleophile. So that's going to attack the hydrogen, and that's going to form the double bond in between the 2 rings. It's going to be from the beginning here when we took the proton off in the first step. Yes. So the OH took that H from the H2SO4, so now we have HSO4 minus, so then we can use that as our new nucleophile. You could also use H2O as the nucleophile, because we did form an H2O once it left in kind of the second step. So you could do HSO4 minus or H2O as your nucleophile. And then on the other side, it's going to be the same thing, just another elimination reaction. And this time we're just going to pull from a different hydrogen. So again, you could use HSO4 minus, or you could use the H2O. That's going to take the hydrogen, and that's going to lend its bond to form the double bond. Okay, any questions on this mechanism? Yes, because if we did the methyl shift, that's a good question. If we did the methyl shift, we'd go from 1, 2, 3, 4. Yes, so we would linearize the chain a little bit more. But however, you can see that that kind of doesn't really make sense with the product that we have. But then also, this is just going to be a secondary carbocation, whereas when we did the hydride shift, it formed a tertiary. You wouldn't be able to pick and choose in this case. Again, kind of just using the product as the guide. But in this case, I think the reason why she specifically drew these 2 products is because the tertiary carbocation is more stable. So the mechanism is going to favor that. Oh, yeah. Okay, yeah. I thought you were saying you could choose to do either one. No, yeah, you're right. Yeah, it doesn't matter. It's on that same carbon there. I'll zoom out. But yeah, if you had done the forming the primary carbocation and then hydride shift, you would get points off. So just be very careful with your mechanisms. If it doesn't really make sense, like a primary carbocation doesn't really make sense, then just double check. Any other questions on the mechanism? Yeah, so basically, if you're doing your mechanism and you form something that doesn't really seem like it makes sense, like a primary carbocation, we know that those are really unstable, so it doesn't really make sense for us to form that in our mechanism. So if you kind of find yourself like questioning what you're doing, maybe more so than usual, then just maybe try and go back and check and see if there's anything else you could do instead. So maybe like use a different nucleophile or see if you need to do a hydride shift or bond shift or something like that. Yeah. Yeah, it wouldn't. I don't think the whole mechanism would be wrong, but I think you'd get a couple points off. I think it says -4 points. So yeah, a little bit more than a couple. Yeah, I'm going to go ahead and move on to synthesis. Okay, so for synthesis, your big ones are going to be Grignard. And for Grignard, we need a carbonyl. We need a MgBr reagent. And we need then H3O plus over the arrow. So as you guys are taking the exam, especially if you guys are struggling with synthesis, what I liked to do when I got to my exams was before they like told you could start, there's like the blue or like purple paper or green paper or whatever on the front. And I would just like brain dump a ton of information on that. So then I could just get to my exam and kind of have that as a reference. So this might be something that I would like write down on that front sheet while we're waiting for the exam to start. And so this is just like the very basic materials you need for a Grignard reagent. Grignard reaction. Another one that you're going to need to know, obviously all of your addition reactions, usually like PBr3, maybe HBr. Make sure you remember your kind of SN2E2 mechanisms because you might have to form like a double bond or something. Another useful one is the acetylide anion reaction. So we saw this one in the reaction section. So this one is just a triple bond carbanion with a carbonyl. And this one kind of does a Grignard style of reaction where it forms a carbon-carbon double bond. And then your oxidation ones are going to be very important. So for the purposes of synthesis, I would memorize two specific reagents. So the first one is going to be Jones for oxidation. The first one is going to be Jones. And so that's going to turn alcohols into ketones and carboxylic acids. And the other one that's like almost even more important than Jones is PCC. So this one's going to turn alcohols into aldehydes and ketones. So this one's really important because if you use Jones to form an aldehyde, it's going to be counted wrong because the strong oxidation reactions, they will not stop at an aldehyde. They would keep going. So your synthesis would technically be wrong if you use that reagent. Yes. Or sorry, yeah. I should clarify. Good point.
That depends on the type of alcohol, it's primary, secondary.
Yeah. I'll show you with this synthesis because it's actually our first step. So like Hamza said yesterday, for these synthesis, you are going to have to break up your molecule because she's obviously not going to let you start with just like a 8-carbon chain. So you're going to need to know your carbon-carbon bond forming reactions. And so usually the product of those reactions are alcohols. So you're going to want to get back to an alcohol so you can do those carbon-carbon bond forming reactions. So for this first one, we see that we have an aldehyde at the end of our chain. And so to turn that back into an alcohol, we're going to need to use an oxidation reaction. But since this one is an aldehyde, we're going to use PCC. If we had done Jones, this would turn the aldehyde all the way to the carboxylic acid, which would be wrong. Since we just want the aldehyde, we're going to use the milder reagent, which is PCC. So now that we have an alcohol, we can do a carbon-carbon bond forming reaction. So we're going to use like Grignard or something like that. So in this case, we could do a split here where we use like a formaldehyde, which would be this, a single carbon. But there is another reagent that we could use, and that would give us a split at this carbon here. And so that's going to be our reaction with an epoxide. And remember, we need either the epoxide, here, I'll put, or the double bond oxygen, and then our other half is going to be our Grignard reagent. So that's going to be MgBr. So when these two react, the Grignard will actually attack at 1 carbon of that epoxide, and then the oxygen gets kicked out, kind of like it does for a regular Grignard, but it just creates the alcohol an extra carbon away because of like the structure of the epoxide. So this one's really useful when you want to form an alcohol like an extra carbon away from the carbon that your M2Br is on. So then to form an epoxide, we're just going to use MCPBA. And so that one turns our double bonds into the epoxide. And I probably should have looked at this at the start, but remember, look at your instructions. Alcohol has alkynes of 3 carbons or less, so this is 2-carbon alkyne, or sorry, alkene. So this one's good to go. Then for our MgBr, we need to do Mg ether to turn it back into the bromine. And then from here, we can do PBr3 to turn the bromine back into an alcohol. And so this is a 5-carbon chain, so we're not short enough yet, so we have to do another Grignard. So we're going to cut it here. We're going to have CH3, C double bond O, H. And then our other side is going to be our Grignard reagent, 3 carbons long. And then don't forget over the arrow, then H3O plus. For the left-hand side, again, we're left with an aldehyde. So in order to turn it into the alcohol, we're going to use the mild reagent, which is PCC. If we had used Jones again, that would turn the primary alcohol into a carboxylic acid, and that's not what we want. That would be wrong. The other side, again, Mg ether. We have bromine in our 3-carbon chain. And then we need alcohols or alkenes. So for this one, we can just use PBr3, and we can turn it into our propanol. Any questions on this synthesis? Sure. I'll zoom in to the last one, and then I'll zoom out for anybody that wants to like get the whole thing in just a second. Okay, so like I said, I'm gonna do an extra mechanism and synthesis, but you don't have to stay for that if you don't want to. What time is it? Yeah, yeah, I was just thinking, sorry. Yep. I'm just gonna go ahead and move right on to the bonus mechanism of synthesis. So Alex, Hamza, James, if you guys want to take questions, like maybe out in the hall for people who don't want to stay, that'd be dope. I just don't want to waste y'all's time if you're not gonna stay for that extra one. Okay, so yeah, so again, I'm going to go over an extra mech and synthesis. So stay if you want to. Otherwise, we'll do questions out in the hall. And then we're also going to do like another study session Thursday in the library from 5:30 to 8. 221J, same place and same time as last time if you came. So just feel free to come and hang out and study with us. I'm honestly not sure what I'm going to do for it this time. I'll have to think, but there's a Teams channel that we have for me and Hamza. I can add you guys. Or I can add you to that. Yeah, that'd be great. Yeah, I mean, there's gonna be people talking. So that's okay. I have to add you. So. So do your student email because it doesn't like.
Like Lily said, anybody who has questions will be out in the hall.
So we're gonna take like a couple-minute break before we get into the bonus. So, but after that, if you guys could take your questions into the hall, because I don't want it to be too loud in here. And if you guys need to be added to the teams, come up and I can add you. Make sure to use your student email. It doesn't mind emails outside of. Sorry? I'm not going to. I'm going to do this one as well. And we're doing the 2016 mech and synthesis. So I forgot to print some stuff out, but you guys probably just have it on your iPads anyways. iPad kids. No, somebody's in the bathroom probably. While we're waiting just a couple minutes for people to come back from the bathroom, do you guys have any questions on anything we did for the first exam? Yeah. We're just waiting for a couple people. They went to like go get water and stuff, so trying to break this awkward silence. So you're gonna put excess if you do a Br2 light reaction. So usually that's gonna be if in the instructions it says work it back to an alkane, because usually you're gonna use an alkane. You're gonna add a Br so you can start doing other stuff to it. But you're gonna have to read your instructions very carefully. Again, because she can ask for different stuff. So even for the exams that you guys might be looking at now, it's like cycloalkene, cycloalkane, hexanol, alkane, alkene, alcohol. So you have to be really careful about what she says. And then just based on the fact that for the last exam, she gave you really specific starting materials, like actual like named compounds. Yeah, it was like I've never seen that before. So just make sure you're really reading your instructions, because it would be very sad, because it's already tough to remember all the different ones that you could go back to, because a lot of people, I think, just assume that you go back to the alkane, which is not necessarily true. So you just got to read your instructions to make sure that you don't miss that. Yes. So like, for example, like based on like the last exam, she could have been like, work it back to ethene, ethanol, propanol, so like very specific reagents. So yeah.
My workshop students just to read. You start by this.
Like, yeah, I would actually go through and like physically underline it so you like remember to actually read the instructions. And you guys can bring like whatever highlighters and stuff that you want to. So okay, I'm gonna go ahead and get started. So we're doing the 2016 exam 3. So this one's kind of funky looking. So for this one, we kind of have a similar situation to what we had in the previous mechanism. We have an acidic condition. We have a double bond, which could be our nucleophile. We also have an oxygen, which could be a nucleophile. So for this one, kind of like what we talked about in the previous mechanism, oxygen is generally a stronger nucleophile, but then also epoxides are super reactive because in addition to having lone pairs on the oxygen, the epoxide has that ring strain in that cyclic triangle structure. So this one's going to want to react and break that ring strain. So for that reason, I'm going to use the epoxide oxygen as my nucleophile. And so I'm just going to have that take the H plus and get protonated. So my first step is just going to be protonating the oxygen of the epoxide. And then from here, we can do some other stuff. So we see that we went from this one cyclopentane to an additional cyclopentane. So what I'm going to do for this next reaction is I'm going to use the double bond as a nucleophile, and it's going to attack the epoxide. Then our OH plus can be a good leaving group and get kicked out. And so for this one, I know that I'm going to need to form a pentane. So I'm just going to number my carbons and make sure that I have everything in the right spot. So I'm going to go 1, 2, 3, 4, 5, and then 1. Okay, so I don't think that's going to give me the big enough ring, so I'm actually going to have this attack at the other side. And so now when I number my structure 1, 2, 3, 4, 5, 6, 1, 2, 3, 5, 6. So it looks like we created the bond between 2 and 6, which looks good in this structure here. And then again, the OH of the epoxide gets kicked out since OH plus is a good leaving group. So now I'm just going to use the product as a guide to kind of guide my drawing, because this is kind of whack. But we have our 2 cyclopentanes. We know carbon 6, it's got these 2 little methyl groups. And then carbon 5. Carbon 5 is going to have our OH because it got kicked off of 6, and it's going to stay on carbon 5. So we have our OH here. And that looks like it makes sense with the end product. And now we just have to make sure that we put the plus charge in the right spot. So the double bonds between 1 and 2 that I numbered attacked the epoxide. 2 is connected to the new ring, so it gained that bond back. So the plus charge is going to end up on carbon 1, which if we look at the end product, that kind of checks out because we have this OH that added at that position, and we have the double bond that was added next to that position. So then from here, in order to get to the first product, we can just do an attack by water. So water is going to attack at that plus charge. We're going to add OH2. And then our last step is just going to be deprotonating that water to form the alcohol. And so that's going to be the product of, that's going to be the first product. Any questions on that first product? Okay. Next one, we already have that plus charge on that tertiary carbon. We just have to form a double bond. So I'm just going to redraw it real quick. So from here, we see that we have a double bond going down towards the first cyclopentane. So we're just going to do an elimination reaction. So you can use water. It's going to take off the hydrogen. That hydrogen is going to donate its bond in to form the new double bond, and that's going to be our second product. Okay, any questions on this mechanism or mechanism in general? Let's see. Yeah, sort of. So again, identify your nucleophiles and electrophiles. The electrophile is generally more obvious because usually it's given to us like this, like our acid. But for this one, I identified my nucleophiles as the double bonds and the oxygen. And then between them, I used my knowledge of the lone pairs on the oxygens generally being a better nucleophile than a double bond. And then also epoxides are very reactive, so it's probably going to be the oxygen in this case that I'm going to pick. Kind of like I mentioned earlier, if it feels like you're drawing something that doesn't make a lot of sense, like a primary carbocation, just go back and double check what you've done so far and see if there's any way you could do something different, or if you could do something like a hydride shift or a bond shift, methyl shift, whatever. And then always use the product that you have on your page as a guide. So for after this first step, I saw that I'm going to go from the linear chain and I'm going to form a new ring. So I kind of used that as my guide, and I was like, okay, now I can use the double bond as a nucleophile to attack the epoxide carbon and form the new ring. So kind of just stuff like that. You know, just making sure you're always checking between what you have and the end product and kind of seeing if you're on track. Because sometimes you just get so caught up in what you're writing that you'll get a few steps down and then you just realize it doesn't really make sense. So like after every step, just, you know, kind of checking in and making sure, okay, this is getting to where I need to be. So it's not, you know, I can't tell you the answers or what it's going to look like, but those are the steps and like the strategies I used when I took it. Okay, I'm gonna go into synthesis. What are you guys feeling worst about for this exam? Which section? Mechanism and synthesis? Reaction.
The overwhelming amount.
Yeah. Reactions. Facts. Yeah, don't forget your facts. I know a lot of you are probably just looking at your reactions right now, but make sure you do go check your facts kind of questions. Yeah. You got this. I believe in you guys. For synthesis, for this one, so in this case, we don't have an alcohol. and we don't have a carbonyl that we could turn into an alcohol, but we're still going to have to form a carbon-carbon bond somehow. So don't forget, also, I always forget to do this first. Cyclohexanol and alcohols of 4 carbons or less. And then the rest of that statement, any oxidizing reducing agents, blah, blah, blah. That's just like the reagents that you can use for the reaction. This is going to be the big part. So for this one, I see that we have a double bond, and I know that one of the reactions that we can do to form a carbon-carbon bond is with an acetylide anion. So instead of doing a Grignard, I'm going to do the acetylide reaction, which is Grignard. Oh, actually, I changed my mind. Ignore that. Pretend I didn't say anything. I forgot. What we can do is, we can turn this into an alcohol. So we're going to do CH2, CH2, CH3, CH3. So we're actually going to turn this into an alcohol by the dehydration mechanism. So this is going to be H2SO4 in heat. And so now we have an alcohol that we can do the Grignard with. So this one we're just going to cut there. Remember, we need our then H3O plus over the arrow. So the left-hand side did not have the alcohol part, so this is going to be our Grignard reagent part. So we have that chain up there, and then in that place we have the MgBr. On the other half, we had the alcohol, so this is going to be our carbonyl half. We're going to have our CH2, CH3 on that side. Working the left side back, Mg ether to form our Grignard. So that's just going to be Br, CH2, CH2, CH3. So for this one, what we've been using a lot has been PBr3 to turn an alcohol into a bromine. But remember that PBr3 only applies to primary and secondary halides. And if we look at the halide that we have here, it's got 1, 2, 3 carbon bonds. So this one's going to be tertiary. So in this case, we won't be able to use PBr3. And so the reaction that we're going to want to use to form a tertiary halide is going to be HBr, ether, and at 0 degrees Celsius. So this one's a little bit unique, but it is on your reaction sheet. So just remember, don't forget about this one. So now that we have our alcohol, we need to work it back to cyclohexanol for alcohols of 4 carbons or less. So this is still not an acceptable starting material. So we're just going to do another Grignard reaction. So we can cut it there. Over the arrow, we have our then HCO plus. So the cyclohexane part had our alcohol. So this is going to be our carbonyl. The CH2, CH3 had our nothing, so it's going to be our Grignard reagent. So we need to work it back to cyclohexanol. So for this one, we can just use Jones and turn that carbonyl into an alcohol. So this one's done. It won't in this case because this alcohol is secondary. So it has 2 carbon groups. So it'll just go to the ketone. It's whenever you have a primary alcohol that you have to be very careful. So then the other side, we have our Grignard, so we can just use Mg ether to turn that into the halide. And again, we're working with alcohols, so we are going to use PBr3. In this case, we can use PBr3 because this is a primary. And so we're just going to turn that back into the alcohol. And it was 4 carbons or less. This is 3 carbons, so we are good to go with that one. Now we have to finish with the right-hand side that we had up top. So this is the ketone. Again, we can use Jones because this is secondary. So we're going to have this 4-carbon alcohol. And if you'll remember, 4-carbon alcohols are allowed for starting materials. So this one's good to go. Okay, that's that synthesis. Reese Jones. So I'm gonna call it here. You guys are free to go, and you guys are free to come ask questions if you have them.